All right, so a big part of chapter 8 is learning how to calculate energy produced or power produced by different power plants. And the simplest power plants are ones that burn fossil fuels. And most power plants after fossil fuel power plants run quite similarly. It's just what turns the turbine is going to be different. So let's just go through the schematics. You need to be able to draw how a power plant is structured, and you need to be able to label the important components of it. So the end product, our secondary energy, is electricity that goes to the power lines. But how we make it follows a sequence of events. So our primary energy source in this case is coal. And outside of a coal power plant, you would have mountains, like literally giant hills or mountains of coal in a field. And you have a conveyor belt that sends that coal at a rate, like we solved in the previous problems. Kilograms per second are being controlled into a furnace, okay, where we're going to be burning that coal. And you have to pump a lot of oxygen in order to burn that amount of coal and make sure that it's releasing all its heat. And then the heat released from that burning of the coal is going to be going into water. So there's a boiler here. It doesn't look like just a bunch of pipes. Usually it's a big container with water in it. And the flame heats the water and turns it into steam. And that steam increases the pressure and flows through a turbine. This turbine turns, and when it turns a coil of wire through a magnet to generate electricity, to generate a voltage. And the faster that turbine turns, okay, the greater the voltage is going to be. So, and that energy, that electrical energy, can then be transmitted through power lines. It'll be transformed to a different voltage to make sure that that electricity is transmitted efficiently through power lines. But in order for that steam to flow, it needs to be cooled and condensed on the other side. Otherwise, it would get plugged. So you have a condenser, a cooler, that cools the steam to create low pressure down here so that the steam will want to flow through the turbine quickly. In order to condense it, you need to have cold water running through the condenser, and that usually comes from a river source. That makes it a lot cheaper. If I have a cold river running by a coal power plant, I can cool it with river water. And then that cold water can then come back into the boiler that is in my steam system, and it's going to then heat up, turn into steam again, and this whole thing can cycle. Okay, so what are the energy conversions that take place in a coal power plant? Well, first of all, my primary energy source, coal, is going to have chemical potential energy. Oops. Which is going to be converted here into thermal energy. Okay, which is then going to be converted into thermal energy of the water. Okay, and another way you can look at it in terms of that water is going to raise its temperature until it changes its phase and becomes steam. So yeah, I can have thermal energy of water. And when it becomes steam, okay, I can say that now that becomes potential energy, right? Because you got to do a phase change. Okay, so the steam is going to have now potential energy. All that thermal energy is converted into potential energy. And the steam has pressure. And as that steam is being condensed, all that potential energy that it has and pressure is going to be converted, into mechanical energy of the turbine. So this turbine that is connected to an electrical generator needs to turn, and that turning is mechanical energy, okay? And then that mechanical energy is converted into electrical energy. Now, as you see here in this flow chart, every energy conversion results in loss, okay, or dissipation. So at every step along the way, I have energy loss, okay? But it's not lost. The energy is dissipated. I can never spell dissipated. Okay, so it just goes out into the environment. So every little arrow that we have here, we have some energy loss or energy dissipation, which would mean that my final amount of energy, all that chemical potential energy, will not be converted 100% into electrical energy. We have loss along the way. So if I was going to design the perfect electrical generator where I can get 100% of this, I need to skip all these steps. And right now that is impossible in the design of a coal power plant. Okay, so the more of these conversions, the more energy loss. That's something you need to know. And IB wants you to write dissipated, not energy loss, because energy can't be lost. It's just transformed from one thing to another. So we need to practice using the word dissipated. Okay, and I can draw these energy conversions in the form of a Sankey diagram, like you can see in the textbook. A Sankey diagram is an engineer's way of keeping track of where this energy went. Okay, so they usually draw it on graph paper. Okay, but what you'll have is something that looks like this. Oops. And, and one more arrow or so. Okay. But I shouldn't have a straight line here. Struggling drawing this on my iPad because it's trying to automatically change the lines. Okay? So if I just make that more straight. There we go. Okay, so the length of this line, like I talked about in class today, this is going to be the energy in. Okay, so that's all the energy that goes in. So for example, it would be all the energy stored in the coal that's going in, the theoretical amount of energy. That's what that line represents. That would be 100% is the width of that line. And this line over here, the width of that line is going to equal to the energy / power that comes out as electricity. That's the useful power. And as we can see, that width is not the same as that width. So the fraction of that width divided by that would tell me the percentage. Now, if I took a ruler out and measured that, I would say that that's probably around 25%. Okay, if this was 10 centimeters, that would be 2.5 centimeters in width, and that's 25%. So it's really important that when you're drawing the Sankey diagram to show the energy flow, you need to use a ruler and you need to draw everything to scale. So that would be like 25%, that would be like 10%. Okay, now we're at 35. That would be like another 25%. Okay, now we're at 60, and then that would be, let's say, another 40%. As you can see, I didn't draw everything to scale. So all these width I would measure with a ruler to be able to calculate what the percentages of are. This arrow that's coming out is the useful energy that we're using, like electricity. And these arrows are the dissipation of heat. So this arrow in my coal power plant, let's call that the friction from the turbine. So that is the energy loss due to friction. Okay, or the energy dissipated due to heat, due to friction. Okay, where else would I lose quite a large amount of energy? Well, I'd lose quite a large amount of energy by trying to condense the steam back into water, right? So that's heat dissipated in the condensing of steam into water. Okay, and this last little bit would be the energy that is dissipated to the environment just by heating up the whole furnace and going out into there so that I don't create enough pressure to explode my furnace. Okay, so heat is going to be released into the environment just from not being able to capture it by the water. So then that would just call that like radiated heat. Okay, and all of these widths will add up to 100%. So it's just a Sankey diagram is our way of tracking where all the energy is going in a power plant. And ultimately, I want my power plant to have an arrow. The output arrow for electricity should be the same width as the input arrow, but that's impossible because we always have to cool things down in order to keep things moving. You have to condense that steam, so it would be just impossible. So at best, we could probably get it to 50%. All right, so you'll have a lot of practice drawing these Sankey diagrams to track the flow, and you need to be able to create a flow chart of energy transitions in order to understand how many arrows will go into that Sankey diagram. All right, so how do we calculate the efficiency of a coal burning power plant? Well, in the Sankey diagram, the useful energy that comes out is here, and the useful energy that comes in, I just take the ratio of that. So if I can find the ratio of useful energy out, or power out, divided by total energy in times 100%, and that will then tell me my efficiency. Okay, so for the example above, if it's 25%, that means that 25% of the energy is coming out. So 250 megajoules versus 1,000 megajoules going in. Okay, that would be a 25% efficient coal power plant. Okay, so let's take a look at some sample problems and see how we can do some calculations with power plants. Okay, the first problem here talks about a coal power plant that burns anthracite, and it produces 400 megawatts and operates with an efficiency of 35%. So draw a Sankey diagram illustrating the energy flow in this power plant. So to draw the Sankey diagram, I would draw a line like this. And remember, you have to measure that line. Okay, so let's say that that line is 10 centimeters. I'm lying because I didn't measure it. Okay, which means that the width of my power outage, the power that it's going to come out, needs to be, let's call that 3.5 centimeters. Okay, so 3.5 centimeters divided by 10 centimeters is 35%. So that's my useful power out. Okay, and then I just have to draw the other arrows. For example, the energy loss due to condensing the steam into water, and the energy loss due to friction in the turbine, which is a smaller amount, and then the energy loss due to heat escaping the furnace. Okay, and I would label all these different points, and the widths, again, tell me the fraction or the percentage of energy that's lost due to that form of dissipated heat. Okay, so I would label that. All right, calculate the rate at which thermal energy is provided by the burning of coal. Okay, so the rate at which thermal energy is provided by the burning of coal, okay, all I was given was the power out. The useful power out is 400 megawatts, and the efficiency is 35%. So how do I go backwards? Okay, well, I need to know that it's not 450, it's 400. 400 megawatts is equal to 35%. So then 400 megawatts divided by 0.35 is going to be equal to the total power in. Okay, another way of saying that is 400 megawatts is equal to 35 over 100. Okay, that's the ratio. So if I wanted to find X, which is the total power in, okay, I just did it all in my head, but if I would set it up like this to solve for X. So then 400 divided by 0.35 is going to be equal to X. Okay, I just moved this over here, and I took 35 divided by 100, which is 0.35, and moved it down there. And then that gave me this relationship to be able to calculate the total power in. So if I put that in my calculator, I think I have an idea of what it is. 400 divided by 0.35. Wow, that's a lot. That gives me 1,142 megawatts Okay, that is going in. Yeah. All right, and let's see. Using that, calculate the rate at which coal is burned in the power plant, assuming the specific energy of coal is 30 megajoules per kilogram. Okay, so what I solved from the last problem is that that's how much energy is being provided by the burning of coal. So 1,142 megawatts is power of burning coal. Okay, and a kilogram of this coal produces 30 megajoules. So then 1,142 megawatts divided by 30 megajoules per kilogram is going to give me, okay, remember a megawatt is megajoules per second. So I'm going to convert that just to so you guys see it. So megajoules per second. So the megajoules cancel, and I'm going to be left with 38 kilograms of coal per second is being burned. Okay? That would be the amount of kilograms that has to be pumped in to this power plant. 38 kilograms per second is being dumped into the flames to be able to produce that power. Okay? All right. And then assuming 50% of thermal energy produced by the burning of that coal goes to water in a river, calculate the flow rate of the water in the cooling pipes such that the temperature of the cooling water never rises more than 5 degrees Celsius. This is a super complicated problem, but not that difficult. We can solve it. But just to go back to the diagram, what they're talking about here is that water from the river is being used to condense that steam back into water, okay? And it'd be a serious problem if that water heats up too much. It's going to kill fish and things inside of the river. So we don't want that water to change its temperature more than 5 degrees. Otherwise, you're going to really damage the life that's in the water. So we need to figure out how fast or how many kilograms per second of water we need to pump through here so that it doesn't ever reach a really high temperature. If we change the flow rate, we can affect the temperature, okay? And it's saying that 50% of the heat energy that goes in is going to be coming out to heat this water. All right, so let's take a look. So how do I do this? So I know that the total power that's going in is 1,142 megawatts, okay? So 1,142 megawatts is the power of heat energy going in. Okay, and this is asking me for if 50% of that heat energy is being then put into the water. Okay, well, this isn't really energy, this is power, but I'm using that to start off with. So then 50% of that is going to be, so 0.5 times 1142 megawatts is going to be equal to 571 megawatts of heat power removed by water. So that's the power of heat going into the water. Okay, so here I just want us to remember when we're talking about a temperature change of 5 degrees, there's a formula we use called Q equals mc delta T. So if I know the heat that went in and I know the mass of the water, I can then calculate the temperature change, which is going to be 5 degrees. Okay, but we don't have M and we don't really have Q. We have power. The power that's going in is 571, but we don't have M. We don't know the M. It's not asking me for M. It's asking me for the flow rate. It's asking me for M over T. So I can calculate Q by taking power times time. Okay, that gives me Q over, which will then be equal to mc delta T. And if I remove time here and I put it down here, this is interesting. M over T is flow rate. It's my mass flow rate. Okay, that's what they're asking me. How many kilograms per second of water needs to be heated in order for that temperature change to only be 5 degrees? So if I rearrange that equation, and I have a new equation where the power of heat going in is equal to the mass flow rate times the specific heat capacity of water times the change in temperature of the water. So the question is asking me to solve for that mass flow rate. So then if I rearrange the equation, power divided by the specific heat capacity times the change in temperature is equal to my mass flow rate. Okay, so if I go up here, 571 megawatts divided by 4.19 kilojoules per kilogram. Okay, this is important. Do you see what's happening here? I got kilojoules and I got megawatts. I don't like that. I have two different units here. I'm going to have to work with that in a second. Okay, times 5. The change in 5 degrees Celsius or 5 Kelvin will be the temperature change, is equal to my mass over the time. I'm going to change megawatts into megajoules over seconds. Okay, now I want to make these common units. So I'm going to convert megajoules into kilojoules. And I can do that by adding 3 zeros here. So 571,000 kilojoules of heat energy per second divided by 4.19 kilojoules per kilogram times 5 is going to give me my mass flow rate. So let's put that together. All right, so we're talking 27,255 kilograms of water per second needs to be flowing into that power plant, okay? Or 27 tons of water per second need to be flying into that power plant, okay? That's huge. That's really, really huge. That's a lot of water. So you're going to be pumping tons and tons of water into that power plant, right, in order to prevent it from overheating. So that's about 27 cubic meters, I think, of water that's going to have to go into that power plant to cool it down per second. Okay, so you'll have a massive pump pumping that water into it. Okay, so this problem, all these problems that I went through are actually in the SOCOS textbook. I've just taken them from there. So you can go take a look at those problems and work through them again with this video and make sure you know how to use all these percentages and unit conversions that I did here, because the problems will never be any different than that. All right, good luck.